Welcome to sitza.com. Meta-directing groups. When you attach the C double bond OH to the benzene ring, we find this is electron withdrawing group. Okay, the C double bond OH. This is an electron withdrawing group because when this double bond over here, which is in conjugation with the benzene ring, due to the resonance, what will happen? This pi electron will shift towards oxygen, and the electrons from the ring that will shift towards this carbon here. And what you get a canonical structure, a resonating structure like this: carbon oxygen, now a single bond, a hydrogen here, and now this particular carbon is going to form a double bond with this, right, with this particular benzene ring, and you have a double bond here, double bond here. Since this particular carbon, it has lost an electron that shifts towards the carbonyl carbon, so therefore it gets a positive charge. So that means the ortho position is positively charged. And then you can further delocalize it. Okay, you can delocalize it like this electron pair goes here, and then in that case what you will see, we find that we have a positive charge over this position, the para position here, and you get here a double bond carbon, single bond oxygen, and a hydrogen over here. And then we can draw one more resonating structure over here, where you can remove this electron, you can delocalize this electron and shift towards the carbon, this positive charge carbon. And therefore what you will get, you get an intermediate like this. Double bond will be formed here, and double bond is here. We have a double bond carbon, single bond oxygen with negative charge, and a hydrogen. And this particular carbon over here, this one, it has lost electron, so it gets a positive charge. And when you delocalize it, again this electron pair goes down, forms a double bond, and it goes back. So what you get the first one back, right? You get the first one back. So what we find, due to the resonance here, when you attach a C double bond OH group to the benzene ring, the groups, the positions at the ortho and the para positions in the benzene ring, these are positively charged. So this electron withdrawing group, it takes electrons from the ring, and that creates a positive charge at the ortho position, para position, and again in the ortho position. So that means when you attach any group that is electron withdrawing, and if it withdraws electrons from the ring, so that it creates a positive charge at the ortho position, para position, and the ortho position. So electrophile, which is electron deficient, it will not attack on these positions. It's going to attack only at the meta position. So this group here, which is electron withdrawing group, when it takes electrons away from the ring, so that electrophilic aromatic substitution reaction that will take place only at the meta position. So this group is called as a meta directing group, right? This is a meta directing group. In the same way, if you attach a this C double bond OR, which is a ketonic group, this will also withdraw the electrons from the ring, and that will also create a positive charge at ortho and the para positions. Esters also, we have a carbonyl group. It again takes electrons from the ring and creates a positive and the positive charge at ortho and the para positions. So therefore electrophile will only attack at the meta positions. So these are the meta directing groups. But say these are the moderately deactivating groups. Okay, why we call it as a moderate deactivating groups? We have strong deactivating groups also. Our ring deactivator is a group that will decrease the reactivity of the of a molecule towards the electrophilic aromatic substitution reaction. We have learned in the electrophilic aromatic substitution reaction, when you suppose take a benzene ring, and if you replace here a hydrogen by any electrophile is electron deficient, and it can attack on any of the carbon atoms or a benzene ring, because all the positions in a normal benzene without any substitution, all the positions are equivalent, so it can carry out a substitution at any of the carbon atoms. And if you compare here the attack of electrophile on the ring and the electrophile on this ring, which is attached with an electron withdrawing group, which is attached with the meta directing group. So we have a C double bond OH, which is electron withdrawing, which is a meta directing group. So when you look at the attack of the same electrophile on this position over here, relatively we find that attack of electrophile on the normal benzene without any substitution is faster than when you attach a meta directing group. Correct? Why? Because of the positive charge. This positive charge that will repel this electrophile. The attack will not be so fast. So that's why these are called as ring deactivators. So when you compare the attack of electrophile on the benzene ring, and when you compare the same electrophile attacking on a ring which is attached with an electron withdrawing group, that means which is attached with any meta directing group, right? Any meta directing group. So here the attack of electrophile will be slow, and here the attack of electrophile will be faster. So that's why we call this one, the meta directing groups are also called as, these are also called as ring deactivators, right? These are called as ring deactivators. Nitro group here is a very strong ring deactivator because it will also pull the electrons from the ring, but this one is a strong ring deactivator. Okay, ring deactivator. Aldehyde group, or the this ester group, it also withdraws electrons, but these two are the weak, these two are the weak, or you can say the moderately, these are the moderate ring deactivators.